There's something utterly mesmerizing about looking up at the night sky and realizing just how much we don't know. The universe is a vast, unpredictable place, filled with wonders that challenge everything we think we understand. And few cosmic phenomena capture that mystery quite like the Mice Galaxies NGC 4676. Picture this: two massive galaxies locked in a slow, inevitable dance, their spiral arms stretching out like long, twisting tails, earning them their playful name. But don't let that whimsy fool you. What's happening here is anything but gentle. This is a collision, a cosmic smash-up playing out over millions of years, birthing chaos, reshaping stars, and leaving behind objects so strange they seem to defy the laws of physics as we know them. Now imagine drifting through this celestial wreckage, where the rules of space and time seem to bend. Among the swirling dust and newborn stars, there are anomalies, 30 of them objects that shouldn't exist, yet here they are, hiding in plain sight. Supermassive black holes behaving in ways that baffle astronomers, enormous structures glowing with energies we can't yet explain, and perhaps most intriguing of all, hints of something even more mysterious lurking in the shadows, something that could rewrite our understanding of galaxy formation itself. This isn't just a story about distant stars, it's a detective story, a puzzle waiting to be solved, and you're about to get a front row seat to the investigation. So why should we care about these far-off galactic oddities? Because they're not just curiosities, they're clues. Every strange object in the Mice Galaxies is a piece of a much larger puzzle, one that stretches across the entire universe. By unraveling their secrets, we're not just learning about two colliding galaxies. We're peering into the forces that shape everything, from the birth of stars to the fate of our own Milky Way. And that's what makes this journey so thrilling. Over the course of this video, we'll explore these 30 enigmas one by one, diving deep into the science, the speculation, and the sheer wonder of it all. So buckle up, the cosmos is about to get a whole lot weirder. At the heart of one of the Mice Galaxies, something defies expectations, a supermassive black hole glowing with bursts of ultraviolet light so intense they outshine entire stars. But here's the twist: black holes aren't supposed to shine like this, at least not in this way. Normally, these cosmic monsters lurk in darkness, their gravity so strong that not even light can escape. So what's causing this one to flare up like a beacon? The answer lies in the chaos of the collision. As the two galaxies spiral closer, vast clouds of gas and dust are ripped apart, funneled toward the black hole in a swirling, superheated frenzy. This isn't just any accretion disk, it's a feeding frenzy on a cosmic scale, warped and twisted by the gravitational tug of war between the galaxies. Astronomers have watched in awe as this black hole erupts unpredictably, sending ultraviolet flares arcing across space like lightning in a storm. These aren't the steady, rhythmic pulses we've seen elsewhere, they're violent, erratic bursts, as if something fundamental in the black hole's behavior has been shaken loose. One theory suggests the collision has tilted the disk, causing gas to pile up unevenly before collapsing inward in sudden, searing waves. Another possibility: the black hole might be spinning faster than usual, whipped into a frenzy by the galactic merger, its magnetic fields tangled into knots that spark these brilliant outbursts. But the real mystery is what this tells us about black holes everywhere. If a galactic collision can make a supermassive black hole act this strangely, what else might be possible? Could similar flares be hiding in other merging galaxies unnoticed? Every flicker of light from this cosmic oddity is a clue, a piece of data that could help us unravel the secrets of how black holes grow, evolve, and shape the galaxies around them. And that's just the beginning, because this glowing enigma is only the first of 30 strange objects waiting to be discovered in the Mice Galaxies. Drifting in the vast emptiness between the Mice Galaxies, there's a group of cosmic orphans, planets untethered from any star, wandering the void in darkness. These aren't just any planets, they're rogue worlds violently flung from their home systems during the galactic collision, now glowing faintly with the warmth of their own creation. Infrared telescopes have spotted their heat signatures, revealing something astonishing. Not one or two, but an entire cluster of these nomadic planets, drifting together like a lost family in the night. What makes this discovery so extraordinary is how it defies our expectations. Planets usually form in the orderly disks around young stars, bound by gravity to their stellar parents. But here, the chaos of the merger has rewritten the rules. As the galaxies collided, gravitational turmoil ripped planets from their orbits, hurling them into interstellar space at speeds that would make escape velocity look tame. Some may have been torn from their stars in violent close encounters with passing giants. Others could have been sent spiraling away when their host systems were shredded by tidal forces. The real mystery, though, is how these rogue worlds manage to stay together. They're not just scattered randomly, they move as a loose group, a ghostly caravan traveling through the cold expanse between the galaxies. One theory suggests they were all ejected from the same destabilized system, a planetary family torn apart but still drifting in the same direction, another possibility. They're temporarily bound by their own weak gravity, a fleeting alliance in the darkness before they inevitably scatter forever. And then there's the heat. These planets shouldn't glow at all without a star to warm them. They should be frozen, invisible relics, but infrared observations show something different. Some still radiate the residual heat of their violent births, their cores simmering from the energy of their ejection. Others might be warmed by tidal forces, stretched and compressed as they pass through dense regions of interstellar gas. A few could even harbor hidden oceans beneath icy shells, kept liquid by internal heat, raising the tantalizing question, could life, against all odds, exist in these drifting worlds? This rogue planet cluster forces us to rethink what we know about planetary survival. If worlds can endure, even thrive, in the harshest reaches of interstellar space, what does that mean for the countless others adrift in the universe? Every one of these orphaned worlds is a testament to the sheer power of galactic collisions, a reminder that when galaxies collide, even planets aren't safe from the chaos. And as we peer deeper into the void between the Mice Galaxies, who knows what other lonely travelers we might find? Next up, something even stranger, a structure so vast it shouldn't exist at all. Among the chaos of the Mice Galaxies, there's a cosmic trick of the light so perfect it fools even the most advanced telescopes. Two brilliant quasars, flickering like distant lighthouses, appear to be an identical pair, mirror images separated by a sliver of space. But here's the catch, they're not two objects at all, they're one. What we're seeing is an illusion, a masterpiece of gravitational lensing, where the warped fabric of space-time bends light like a funhouse mirror. This phenomenon happens when a massive object like a galaxy or cluster sits perfectly between us and a distant quasar. The immense gravity of the intervening galaxy acts like a lens, twisting the quasar's light into multiple paths as it travels toward us. In this case, the collision of the Mice Galaxies has created a dense knot of matter, a natural magnifying glass that splits the quasar's light into two distinct images. Hubble's sharp eye has captured this cosmic mirage in stunning detail, revealing the twin quasars glowing with eerie symmetry. But the real magic lies in what this tells us about the universe. By studying the slight time delay between the two images, since one light path is slightly longer than the other, astronomers can map the invisible scaffolding of dark matter warping spacetime. It's like using the quasar as a flashlight to illuminate the hidden structure of the galaxies themselves. And there's more. The lensing effect also magnifies the quasar, giving us an unprecedented close-up of a phenomenon usually too distant to study in detail. We can see the turbulent disk of superheated gas swirling around the central black hole, a view normally reserved for objects in our own cosmic backyard. Yet for all its brilliance, this illusion hides a darker secret. The quasar's flickering patterns don't always match perfectly. Sometimes one image flares while the other stays dim, a clue that the lensing galaxy isn't just a smooth mass. Tiny clumps of dark matter, invisible to telescopes but palpable in their gravitational grip, must be tugging at the light, distorting it further. These discrepancies are like cosmic breadcrumbs, leading us toward answers about the true nature of dark matter. So the next time you see those twin points of light in Hubble's images, remember, you're not just looking at a quasar. You're seeing space-time itself flex and bend, revealing secrets about the universe's most elusive ingredients. And in the grand collision of the Mice Galaxies, these mirages are more than just curiosities, they're tools, helping us decode the invisible architecture of the cosmos. Now shift your gaze to another enigma, one that glows not with borrowed light, but with its own radioactive fury, a star cluster so dense it defies physics. Tucked between the swirling arms of the Mice Galaxies, there's an enigma that gleams like a cosmic scar, a jagged metallic streak stretching across the void, utterly unlike the star clusters and gas clouds around it. This isn't just another celestial oddity. Spectroscopic readings reveal something shocking. The structure is dense with heavy metals, iron, nickel, even traces of gold and platinum, far more concentrated than anything seen in typical galactic debris. It's as if someone took a dwarf galaxy, ripped it apart, and left only its metallic skeleton behind. Theories about its origins split astronomers into two camps. One side argues this is the remnant of a dwarf galaxy devoured long ago by the Mice Galaxies, its stars and gas stripped away by tidal forces, leaving only its metallic core, a ghostly fossil of a smaller system sacrificed to the collision. The other camp points to something more exotic. The structure's unnaturally straight edges and sharp angles don't match the chaotic swirls of a natural merger. Could this be evidence of something constructed? The idea teeters on the edge of science fiction, but the data forces us to ask, what natural process could forge a megastructure like this? Here's where it gets even stranger. The metals aren't just scattered randomly, they're arranged in layers, almost like geologic strata, with heavier elements sinking toward the structure's core, a pattern usually seen in planetary formation, not interstellar wreckage. Some researchers suggest this could be the shattered remains of a super-Earth, a planet so massive it formed its own metallic mantle before being torn apart in the galactic collision. Others propose an even wilder idea. What if this is the carcass of a failed star, a brown dwarf that never ignited, its dense metals left to cool in the darkness? Then there's the timing problem. Heavy metals like these take billions of years to form, forged in the hearts of dying stars or cataclysmic supernova. Yet the Mice Galaxies collision is relatively recent in cosmic terms. How did such a metal-rich structure form so quickly? One tantalizing clue comes from its motion. It's not drifting aimlessly. The megastructure is spinning slowly but unmistakably, as if whatever created it left behind a faint echo of momentum. Could this rotation be the last whisper of whatever cataclysm birthed it? Whether natural or something beyond our current understanding, this metallic monstrosity is a reminder of how little we truly know about the universe's capacity for wonder. Every anomaly in the Mice Galaxies forces us to rethink the boundaries of physics, and this one is no exception. As telescopes turn their gaze back to that gleaming streak, one thing is certain: the cosmos still holds secrets that defy even our wildest imaginations. Now shift your focus to an object that doesn't just exist in the chaos, it thrives in it. Deep in the tangled heart of the Mice Galaxies, something screams into the void, a burst of radio waves so powerful it outshines entire stars for the briefest moment. This isn't just another fast radio burst, those cosmic lightning strikes we've detected across the universe. This one repeats. Like clockwork, every 47 days, the same piercing signal erupts from the chaos of the colliding galaxies, a scream that defies easy explanation. What makes this radio burst so extraordinary is its precision. Most fast radio bursts are one-off events, fleeting explosions of energy that vanish as quickly as they appear. But this one, it's a metronome, its rhythm so consistent astronomers could set their watches to it. The leading theory points to a magnetar, a neutron star with a magnetic field so intense it could strip the electrons from your atoms from halfway across the galaxy. When these cosmic monsters quake under the strain of their own magnetism, they can unleash torrents of radio waves, but even among magnetars, this signal is odd. The 47-day cycle suggests an orbit, perhaps a magnetar swinging around a companion star. Its burst triggered at the same point in its path like a lighthouse beam cutting through fog. Then there's the location. The signal originates from the overlap region where the two galaxies are grinding together, a zone of unimaginable turbulence. Could the collision itself be squeezing the magnetar's magnetic field, twisting it like a rubber band until it snaps back in these predictable outbursts? Or is something even stranger at work? Some researchers have floated the idea of a binary magnetar system, two of these hypermagnetic stars locked in a death spiral, their combined forces creating bursts unlike anything we've seen before. But of course, there's the elephant in the room, the tantalizing, if remote, possibility that this isn't natural at all. The signal's repetition and precision have inevitably led to whispers of artificial origins. Could this be some kind of beacon, a cosmic SOS, or a piece of machinery left running in the wreckage of an ancient civilization? It's a long shot, but the very fact that we're forced to consider it speaks to how bizarre this signal truly is. What's most exciting, though, is what this radio scream reveals about the Mice Galaxies themselves. Every burst carries faint imprints of the gas and dust it's traveled through, like a fingerprint of the chaos between the colliding spirals. By studying how the signal distorts, astronomers are mapping the invisible maelstrom of ionized plasma and magnetic fields churning in the galaxy's wake. These bursts aren't just mysteries, they're tools, helping us piece together the violent story of this cosmic collision. And the plot thickens. Recently, the signal's rhythm has begun to change. The interval between bursts is shortening, as if whatever's producing it is speeding up. Is this the prelude to a catastrophic event, a magnetar crumbling under its own weight, or a binary pair inching toward merger? Or is it just another twist in a puzzle we're only beginning to understand? One thing's certain, as long as that radio scream echoes through the void, we'll be listening, straining to decode its secrets. Now, turn your attention to an object that doesn't just defy expectations, it obliterates them. Hidden in the swirling chaos of the Mice Galaxies, there's an invisible hand sculpting the cosmos, a knot of dark matter so dense, it bends the very fabric of space-time around it. Unlike the glittering stars or glowing gas clouds we can see, this phantom structure reveals itself only through its gravitational fingerprints. The way it warps the paths of nearby stars, the subtle distortions it imprints on distant quasar light, and most strikingly, how it's yanking the galaxy's iconic tails into their twisted shapes. This isn't just a passive lump of unseen material, it's an active architect reshaping the collision in real time. The discovery came when astronomers mapped the galaxy's gravitational field and found something startling. The pull of visible matter alone couldn't explain the extreme curvature of those long, star-studded tails. There had to be something else, something massive and invisible. Supercomputer simulations traced the anomaly to a dark matter clump, weighing in at trillions of times the mass of our Sun, lurking where the two galaxies intersect. Its presence solves one mystery while creating another. Why is this dark matter not so tightly concentrated? Most models predict dark matter should be more evenly smeared across the galaxies like an ethereal fog. Instead, it's clumped like molasses dripping from a spoon, defying our expectations of how this elusive substance behaves under extreme conditions. Here's where things get even stranger. The knot isn't just sitting still, it's moving, plowing through the collision zone like a cosmic snowplow, shoving gas and stars aside with its gravitational wake. This motion explains the peculiar kinks observed in the galaxy's tails, as if an unseen force is tugging them into alignment. Some researchers suggest the knot might be the remnant core of one of the galaxies, a dark matter skeleton, left behind as the visible stars and gas were stripped away. Others propose a more radical idea, that the knot is a primordial relic, a surviving chunk of dark matter from the early universe, far denser than modern versions. The implications ripple far beyond the Mice Galaxies. If dark matter can clump this densely, it challenges decades of simulations predicting its behavior. Could there be entire structures made of dark matter, invisible mountains and valleys hidden in plain sight throughout the universe? And what does this mean for the hunt to detect dark matter particles on Earth? If the stuff is clumpier than we thought, our experiments might need to rethink their strategies. Yet for all its mystery, this knot is also a tool. By watching how it distorts the galaxies around it, astronomers are essentially using the Mice Galaxies as a giant dark matter laboratory, testing theories in ways no Earthbound experiment could. Every star it deflects, every ripple it creates in the galactic tails, is a clue, a breadcrumb leading us closer to understanding the universe's most elusive substance. And just when we think we've grasped its secrets, the knot throws another curveball. Recent observations suggest it might be rotating, spinning silently in the dark like a cosmic vortex. If confirmed, this spin could rewrite the rules of how dark matter interacts with itself, revealing forces at work we've never dreamed of. One thing's certain in the shadowy heart of the Mice Galaxies, the universe is showing us just how much we still have to learn. Now shift your gaze to an object that doesn't lurk in darkness, but burns with a light so fierce it redefines what we thought was possible. Amid the chaos of the Mice Galaxies, the universe staged a fireworks display unlike any other. 3 supernova detonating in perfect synchrony, their light flooding a single corner of the colliding spirals. This wasn't just coincidence, it was a cosmic hat trick, a 1 in a billion event that left astronomers scrambling for explanations. Each explosion belonged to a different stellar class, one a Titanic type Roman 2, its progenitor a massive star collapsing under its own weight, another a runaway type Aya, a white dwarf stealing matter until it crossed the brink of destruction, the third a bizarre hybrid, its light curve flickering between patterns like a misfiring engine. Together, they painted a triple portrait of stellar death, their combined glow outshining entire star clusters for weeks. What makes this trio so extraordinary isn't just their simultaneity, it's what their light revealed. As the supernova's shockwaves plowed through the collision zone, they lit up the surrounding gas like a flashlight in a fog, exposing hidden structures in the galaxy's shared atmosphere. The type Roman 2 blast carved through dense molecular clouds, triggering secondary star formation in its wake. The type Ia's ultraviolet fury ionized vast swaths of hydrogen, creating temporary nebulae that shimmered like cosmic graffiti. And the hybrid, its erratic pulses traced magnetic field lines normally invisible to telescopes, revealing how the galaxy's magnetic architectures were braiding together in the merger. The odds of this synchronicity are staggeringly low. Supernova in Milky Way-sized galaxies typically occur once or twice a century. For 3 to ignite within months, let alone weeks of each other in the same galactic neighborhood, suggests something pushed stellar evolution into overdrive. The culprit, the collision itself. As the Mice Galaxies grazed each other, their gravitational dance sent shockwaves through star-forming regions, compressing gas clouds and stressing aging stars to the breaking point. It's as if the universe flicked a domino chain of stellar time bombs, each one primed to explode under the slightest nudge. But the real treasure lies in the light curves, the precise graphs tracking each supernova's brightness over time. Normally, astronomers study these patterns to classify explosions. Here, they became something more, a diagnostic tool. The Type Roman II curve showed a strange plateau phase, lasting twice as long as models predicted, evidence that it was detonating into a pre-existing shell of gas, likely ejected by its progenitor star just centuries earlier. The Type I's curve flickered with rapid dips and spikes, suggesting its white dwarf had been spinning wildly before detonation, a clue to how binary systems behave under extreme gravitational stress. And the hybrid's erratic pulses, they matched no known model perfectly, hinting at a stellar oddity unlike anything in our catalogues, perhaps a Thorne-Zitkow object, a hypothetical star within a star finally meeting its violent end. This triple blast didn't just light up the sky, it illuminated fundamental questions about how galaxies evolve. The supernova's debris is now seeding the collision zone with heavy elements, future building blocks for planets and life. Their remnants are heating surrounding gas, slowing its collapse into new stars, and their light, still echoing through the galaxy's dust lanes, continues to reveal hidden structures like a cosmic sonar. For astrophysicists, it's a once-in-a-career dataset, a chance to study stellar death in triplicate under conditions no lab could ever replicate. Yet the most haunting question remains, could this happen again? As the Mice Galaxies continue their slow-motion crash, their gravitational tides churn more stellar nurseries and aging giants alike. Somewhere in that chaos, another trio of stars might be ticking toward their own simultaneous demise. And when they go, we'll be watching, ready to decode whatever new secrets their light might bring. Now, turn your attention to an object that doesn't explode with light, but swallows it whole, a black hole binary rewriting the rules of gravitational engagement. In the tangled wreckage of the Mice Galaxies, there's a cosmic magician performing the ultimate disappearing act, a nebula that flickers in and out of existence like a ghost in the interstellar fog. One moment, it's there, a glowing cloud of ionized gas spanning light years, its delicate tendrils captured in vivid detail by Chandra's X-ray vision. The next gone, as if some unseen hand flipped a switch, leaving behind only empty space where vibrant cosmic structures once shimmered. This isn't just a camera glitch or an observation error. The Phantom Nebula, as astronomers call it, has vanished and reappeared 3 separate times over the past decade, each disappearance lasting months before the structure materializes again unchanged. Time-lapse imagery from Spitzer and Chandra tells a story that defies simple explanation. In infrared, the nebula pulses with the warmth of embedded star clusters, their newborn energy lighting up the gas like a lantern. But when it vanishes, even those heat signatures dim beyond detection. The leading theory points to immense dust clouds, opaque curtains of carbon and silicon compounds drifting through the collision zone. When these dust walls pass between us and the nebula, they could act like a cosmic blindfold, blocking all wavelengths from radio waves to X-rays. But there's a problem. No known dust formation is both large enough to cloak the entire nebula and dense enough to erase even high-energy X-ray emissions. That's led to wilder possibilities. Some researchers suggest we're witnessing a rare temporal phenomenon, a gravitational lensing effect where intervening mass distorts not just space but time. Imagine a knot of dark matter warping spacetime so severely that light from the nebula takes multiple paths to reach us, some so delayed they arrive months or years apart. The result, a celestial illusion where the nebula appears to vanish when its light takes the scenic route through the universe's twisted geometry. Supporting this, Chandra detected faint X-ray echoes lingering after the nebula's last disappearance, like afterimages of a cosmic flashbulb. Then there's the composition mystery. Spectral analysis reveals the nebula's gas is laced with elements usually forged in supernova iron, oxygen, neon, but in ratios that don't match any known stellar explosion. One tantalizing clue, the gas is cooling between disappearances as if something is siphoning away its energy. Could this be evidence of an unseen compact object, a neutron star or black hole, periodically ionizing the nebula before retreating into dormancy? Or is the nebula itself a kind of interstellar battery, storing and releasing energy in cycles we're only beginning to map. Every reappearance offers new clues. During its last visible phase, Hubble caught delicate filaments within the nebula vibrating in unison, as if plucked by some immense gravitational cord. ALMA radio antennas traced bizarrely coherent magnetic fields threading the gas, structures too orderly to form naturally in the chaos of a galactic collision. And then there's the most perplexing detail of all. Each time the Phantom Nebula returns, it does so exactly as it was before, down to the positioning of individual gas knots. This isn't just a cloud reforming, it's a cosmic snapshot being unveiled again and again. Whether it's dust, space-time trickery, or something beyond our current physics, this flickering enigma forces us to confront how much we still don't understand about the interstellar medium. The Phantom Nebula isn't just a curiosity, it's a stress test for our models of how gas and dust behave under extreme conditions. And as the Mice Galaxies continue their dance, who knows what other disappearing acts might be waiting in the wings. Now zoom in closer to an object not hiding in gas or dust, but burning brighter than anything else in the collision zone. A hypervelocity star with a trail like a cosmic comet. The Mice Galaxies hold planetary secrets that could rewrite our understanding of cosmic chemistry, none more dazzling than a world literally forged from stardust and pressure. Orbiting a carbon-rich star in the collision zone, this planet doesn't just contain diamonds, it is a gigantic crystalline sphere glinting in the cosmic dark. Found through the subtle dimming of its host stars light a telltale dip that revealed its transit, this world defies all expectations of planetary composition. At first glance, the data seemed impossible. The planet's density was off the charts, far heavier than a world its size should be, while infrared scans showed heat radiating unevenly across its surface, as if vast continents of thermally conductive material were bleeding energy into space. Spectroscopy solved the mystery. The atmosphere brimmed with carbon monoxide and hydrogen cyanide, the chemical fingerprints of a carbon-dominated world. But the real shock came when models factored in the crushing pressures near its core. Under those extreme conditions, carbon wouldn't form mundane graphite or soot, it would crystallize into diamond, layer after layer, until the entire planetary mantle solidified into something resembling a cosmic jewel. This isn't just a static crystal, though. The planet's surface is a dynamic hellscape where diamond mountains rise and fall in slow motion. At temperatures exceeding 2,000 degrees, the carbon crust behaves like a bizarre hybrid of rock and metal, rigid enough to maintain continental-scale structures, yet pliable enough to flow over geologic time. Tectonic forces, driven by the intense heat of radioactive carbon isotopes, push diamond slabs the size of continents against one another, creating glittering mountain ranges that catch the light of its dim red sun. Some peaks may even reach heights where the pressure drops enough for the diamond to revert to graphite, creating soot-capped summits that snow hydrocarbons back into the atmosphere. What makes this world truly revolutionary is what it implies about planet formation. Born from the ashes of carbon-rich stars that died in the galactic collision, it's a snapshot of how extreme environments can rewrite the rules of chemistry. Most planets form from oxygen-rich materials, creating silicates and water. But here, oxygen is the rare element, outnumbered 10-to-1 by carbon. In this alien crucible, rivers of tar might flow beneath skies thick with carbon smog, while underground, the weight of 100 miles of diamond creates liquid carbon oceans at the boundary with the core. Yet the most tantalizing question remains, could such a world ever harbor life? While its surface is undeniably hostile, some astrobiologists speculate about subsurface layers where pressure and temperature might allow for exotic chemistries, perhaps even carbon-based molecules we've never imagined. One thing's certain, this diamond world proves the universe is far more inventive than we'd ever dreamed, turning stellar violence into cosmic art, one crushing megapascal at a time. Now shift your gaze from diamond crusts to stellar pyrotechnics, a binary star system where one partner refuses to die quietly. Nestled within the turbulent embrace of the Mice Galaxies, gravity has crafted its own masterpiece, a near-perfect replica of the famous Einstein cross, but on a far more intimate scale. While the original cosmic crucifix appears when a distant quasar's light is split by a massive foreground galaxy, this miniature version plays out with a different cast, a lone, brilliant star caught in the gravitational vise of two colliding black holes. The result, 4 shimmering points of light arranged in a symmetrical cross, a celestial illusion so precise it seems almost engineered. What makes this phenomenon extraordinary isn't just its beauty, it's the sheer improbability of the conditions required to create it. Gravitational lensing typically warps light into arcs or smeared streaks, not geometric perfection. But here, the alignment is so exact that the black hole's combined gravity acts like a cosmic projector lens, bending space-time into a 4-faceted prism. As the star's light travels toward us, it splits into separate paths, each curving around the black holes at slightly different angles before converging again in our telescopes. The effect is so crisp that astronomers initially doubted their instruments, convinced such symmetry couldn't occur naturally in the chaotic environment of a galactic collision. The secret lies in the black hole's dance. Unlike solitary behemoths lurking at galaxy centers, this pair orbits mere light-years apart, their mutual pull creating a gravitational sweet spot where light behaves in mathematically predictable ways. Simulations reveal their movement is unusually synchronized, a rare stability amidst the chaotic merger. One black hole spins vertically relative to our line of sight, the other horizontally, their counterbalanced rotations smoothing spacetime's wrinkles just enough to forge this fleeting optical miracle. But the real treasure lies in what this replica reveals about lensing physics. The star's 4 images flicker with a slight time delay, mere hours between them allowing astronomers to measure the black hole's masses with unprecedented precision. Even more intriguing, the cross isn't static. Over months of observation, its arms have subtly twisted, a fingerprint of the black hole's orbital wobble as they exchange momentum. These minute shifts let scientists map the invisible contours of spacetime itself, probing regions too close to the event horizons for traditional observation. Yet the biggest surprise came when spectrographs analyzed each point of light separately. The star isn't just any sun, it's a blue supergiant heavy with metals forged in earlier generations of stars. As its light filters through the lensing zone, it picks up spectral imprints from the black hole's accretion disks, revealing their composition. Iron, oxygen, even traces of gold swirl in these unseen maelstroms, elements normally impossible to detect so close to a singularity. The cross has become a prism, splitting not just light but the very secrets of the black hole's last meals. This cosmic quirk won't last. As the black holes spiral closer, their gravitational lens will distort, stretching the cross into unrecognizable shapes before vanishing entirely. For now, though, it stands as a testament to the universe's ability to craft order from chaos, a fleeting alignment where gravity, motion, and light conspire to show us the hidden architecture of spacetime. And somewhere in that delicate balance, there may be clues to an even deeper mystery: how black holes, the universe's most destructive forces, can also become its most precise lenses. Now shift your gaze from this optical marvel to an object that doesn't bend light. It consumes it whole, leaving only silence in its wake. Deep in the war zone between the Mice Galaxies, magnetism has gone rogue. A sprawling region, twice the size of our solar system, crackles with magnetic fields so intense they'd rip electrons from atoms within seconds if you could stand near them. These aren't the gentle, looping fields we see around most stars. These are cosmic tornadoes, twisted into knots so tight they register 100 times stronger than anything in the Milky Way. Hubble's polarized light images reveal them as eerie, glowing filaments, a spiderweb of energy stretching across 400 light-years, each thread humming with enough power to light entire civilizations for millennia. What created this monstrosity? The answer lies in the collision's shockwaves. As the two galaxies smashed together, their interstellar gases didn't just mix, they were hurled against each other at millions of miles per hour, turning entire molecular clouds into particle accelerators. Hydrogen atoms, stripped to their nuclei, spiraled along these newborn magnetic lines like beads on a wire, amplifying the fields exponentially. The result is a self-reinforcing loop. The stronger the magnetism grows, the more charged particles it traps, which in turn pumps the fields to even more ludicrous strength. It's a runaway feedback loop with no off switch, but here's where it gets fascinating. This magnetic maelstrom isn't just destroying, it's creating. The same forces that should rip young stars apart are instead triggering the most prolific star-forming surge ever recorded. ALMA radio telescopes have spotted over 300 protostars nestled along the magnetic filaments, each one sparking to life as the fields crush gas clouds into dense cores. Normally, magnetism stifles star birth by propping up clouds against collapse. But in this extreme environment, the fields have become so tangled they're doing the opposite, acting like cosmic vice grips, squeezing matter until fusion ignites. Some of these infant stars are being born with magnetic footprints stronger than mature neutron stars, their surfaces crackling with auroras visible across interstellar distances. The polarized light data reveals even wilder details. These fields aren't static, they're alive, writhing like snakes in real time. Time-lapse observations show individual filaments snapping and reconnecting in bursts of energy that briefly outshine quasars. These magnetic reconnection events, normally seen on the Sun's surface, are happening here on scales a billion times larger, launching jets of plasma at near light speed. One such jet, caught by Chandra's X-ray eye, punched clean through a neighboring gas cloud, leaving a tunnel of ionized neon glowing in its wake. Yet the biggest mystery isn't the field's strength, it's their structure. Instead of the orderly north-south alignment we see in most galaxies, these lines form fractal patterns, repeating the same chaotic twists whether you zoom in or out. It's as if someone took a Van Gogh painting and scaled it up to cosmic proportions. Some theorists suggest this could be a glimpse of primordial magnetism, a relic from the universe's first seconds frozen in time. Others argue it's proof of undiscovered physics, perhaps a quantum effect where spacetime itself becomes magnetized under extreme stress. One thing's certain, this region is rewriting the rules. Every telescope trained on it finds something new, from stars with magnetic poles at their equators instead of their poles, to gas clouds shaped like perfect cubes by the field's unrelenting grip. And as the galaxies continue merging, this magnetic monster is only growing stronger, a testament to the raw, creative power of cosmic chaos. Who knows what other magnetic miracles or terrors might emerge before the collision runs its course? Stretching like a luminous scar across the Mice Galaxies, there's a river of stars so faint it was nearly missed, a ghostly stellar stream, remnants of a smaller galaxy torn apart and digested in this cosmic collision. Unlike the vibrant spirals or glowing nebulae that dominate telescopic views, this stream is subtle, its stars scattered so thin they blend into the darkness until specialized filters reveal their true extent. But once seen, it's unmistakable, a winding trail of ancient suns, each one a silent witness to the violence that birthed them. Simulations reconstruct the stream's origins with chilling precision. Roughly 800 million years ago, a dwarf galaxy, perhaps 1/10 the mass of the Milky Way, ventured too close to the Mice Galaxy's gravitational pull. As tidal forces seized it, the smaller galaxy stretched like taffy, its stars ripped away in long, looping arcs. Some were hurled into intergalactic space, lost forever. Others settled into elongated orbits, forming this shimmering ribbon that now traces the merger's history like a cosmic timeline, the most telling detail. The stream isn't smooth. Its density fluctuates in distinct clumps, gravitational fossils marking moments when the dwarf galaxy passed particularly close to the Mice Galaxies' cores, shedding stars in bursts like a tree losing leaves in a storm. What's astonishing is how much this stellar river reveals. By measuring the metallicity of its stars, their heavy element content, astronomers can trace their birthplace. The stream's oldest stars are poor in metals, suggesting they formed early in the universe, while younger, metal-rich stars likely originated near the dwarf galaxy's center before its destruction. Even their motions tell a story. Some drift lazily, barely clinging to the stream's gravitational flow, while others race along its length, accelerated by past encounters with dark matter halos. Together, they form a dynamic map of the merger's gravitational tides, a record of forces that shaped the Mice Galaxies into what they are today. Yet the stream's greatest value lies in what it teaches us about dark matter. Its shape, particularly the way it bends and kinks, hints at the invisible scaffolding surrounding the Mice Galaxies. Unlike visible matter, dark matter doesn't just clump at the center. It forms an extended halo whose gravity tugs at the stream like an unseen hand. By modeling these distortions, scientists have reconstructed the halo's structure with unprecedented detail, revealing it's not a perfect sphere but a triaxial blob warped by the ongoing collision. Some sections of the stream even show gaps, silent evidence of dark matter subhalos, smaller clumps that punch through the stellar river like rocks diverting a creek. But the most haunting realization, this stream is temporary. Over the next few 100 million years, the Mice Galaxy's gravity will continue to stir and disperse these stars until they're indistinguishable from the galactic background. For now, though, they remain a fleeting monument to a galaxy that no longer exists, its story written in starlight for those who know how to look, and as telescopes peer deeper, who knows what other lost histories might surface in the collision's wake. Now turn your attention to an object that doesn't drift quietly. It screams across the void with the force of 1,000 suns. In the heart of the Mice Galaxy's collision zone, time itself seems to stutter, and at the center of this cosmic anomaly spins a pulsar that shouldn't exist. Clocking in at nearly 1,000 rotations per second, this neutron star whirs faster than a kitchen blender, emitting radio pulses so precise they could set atomic clocks. There's just one problem. According to every known law of physics, it should have torn itself apart long before reaching such ludicrous speeds. The centrifugal forces at play here exceed theoretical limits by nearly 30%, leaving astronomers with three equally mind-bending possibilities, each more radical than the last. First, the conservative explanation, a glitch. Neutron stars occasionally stutter when their crusts rearrange under intense magnetic stress, briefly speeding up before settling back to normal. But this pulsar's acceleration isn't temporary, it's sustained, its spin increasing by microseconds each year like a cosmic top refusing to slow down. Even stranger, its slowdown rate, normally predictable as pulsars shed rotational energy, fluctuates wildly, sometimes reversing entirely. It's as if something inside is periodically rewinding its energy, defying the universal trend toward entropy. Then there's the quark star hypothesis, a controversial idea suggesting this object isn't a neutron star at all, but something far stranger. Under normal conditions, neutron stars are thought to contain degenerate matter so dense atomic nuclei dissolve into a sea of neutrons. But if the collision's unimaginable pressures compressed this star beyond that point, its neutrons might have shattered into their constituent quarks, creating an ultra-dense quark soup with fundamentally different physics. A quark star's surface could be 100 times smoother than a neutron star's, reducing the drag that normally slows pulsars. Its core might resemble the primordial state of the universe microseconds after the Big Bang, allowing spin rates that conventional matter couldn't sustain. Supporting this, the pulsar's X-ray emissions show a thermal pattern inconsistent with neutron star models, with hot spots that rotate independently of the whole, like blobs in a lava lamp orbiting at their own rhythm. But the most electrifying possibility, that we're glimpsing entirely new physics. Some theorists suggest the pulsar's core might harbor exotic particles unknown on Earth, relics from higher dimensional space compactified during the galactic collision. Others propose it's tapping into vacuum energy, somehow converting spacetime's inherent quantum fluctuations into rotational momentum. The most radical models even entertain the idea of microscopic wormholes threading its interior, connecting moments in time to create a self-sustaining energy loop. What makes this pulsar invaluable isn't just its strangeness, it's how it broadcasts its secrets. Each radio pulse carries subtle distortions from traveling through the star's immense gravitational field, allowing astronomers to map its interior like cosmic seismologists. Recent analysis reveals rhythmic echoes in these pulses, suggesting internal structures vibrating at frequencies no neutron star model predicts, perhaps the quakes of a crystallized quark surface or resonances within an exotic superfluid core. Even its magnetic field defies expectations, twisting into helical coils that somehow amplify rather than dampen its spin. As telescopes continue monitoring this cosmic rebel, one truth becomes clear. The Mice Galaxies didn't just break the rules of celestial mechanics, they rewrote them. Whether this pulsar is a quark star, a portal to new physics, or something beyond our current imagination, its very existence proves the universe still holds wonders that laugh at our textbooks. And somewhere in the precise timing of its next radio pulse, there may lie clues to secrets we've only begun to fathom. Hovering between the colliding galaxies like a cosmic fog, there's a cloud that glows with an eerie blue hue under X-ray vision. Not from starlight or heat, but from something far stranger. It's packed with xenon, an inert gas so rare in space that its abundance here defies logic. This isn't just a wisp of interstellar matter. It's a chemical anomaly, a galactic crime scene where the elemental fingerprints point to an event so violent, it can forge atomic nuclei like a cosmic blacksmith. Chandra's spectrographs revealed the truth. Xenon concentrations here are 50 times higher than anywhere else in the observable universe, a smoking gun for processes we've only theorized. To understand why this matters, picture the universe's elemental factory. Most xenon forms in supernova, where dying stars hurl their guts into space, or in the slow neutron capture processes of aging red giants. But the quantities here, they scream of something far more exotic, a neutron-star merger. When these ultra-dense corpses collide, they unleash a kilonova, an explosion so energetic it can forge heavy elements in seconds through rapid neutron capture or the R process. The cloud's isotopic ratios tell the story. Its xenon isn't the evenly mixed blend of supernova debris. It's lopsided, rich in isotopes like xenon-136, which only forms under the neutron-rich hellscape of colliding stellar remnants. It's as if we've stumbled upon the fallout of a cosmic alchemy experiment, one where gravity and quantum physics conspired to mint elements no star could create alone. The cloud's structure deepens the mystery. Instead of a diffuse sphere, it's shaped like a torus, a donut of gas spinning in the collision zone, its outer edges laced with strontium and tellurium, other R-process hallmarks. This suggests the xenon didn't just scatter randomly. It was funneled outward by the merger's magnetic fields or the neutron star's relativistic jets. Supporting this, astronomers have spotted a faint gamma-ray burst afterglow nearby, a fading echo of the kilonova that might have birthed it, but the real enigma is timing. Neutron star mergers are rare, perhaps once every 100,000 years per galaxy. For the Mice Galaxies to host one during their collision stretches coincidence to its limits, unless galactic mergers somehow trigger these events. And then there's the cloud's glow. Xenon doesn't naturally emit X-rays unless it's ionized, and this cloud is pulsing with them, as if some unseen energy source, perhaps a hidden neutron star remnant, is still energizing the gas. The pulses aren't regular, they're chaotic, like aftershocks from an unseen disturbance. One theory posits a magnetized wind from the merger's leftover core, a spinning neutron star whose magnetic field whips the xenon into glowing. Another suggests the cloud is plowing through a filament of dark matter, its particles annihilating on contact and releasing bursts of energy. This xenon-rich fog isn't just a curiosity, it's a Rosetta Stone for the origins of heavy elements. The gold in your jewelry, the platinum in catalytic converters, even the uranium in reactors might have been born in events like this. By studying how xenon behaves here, we're glimpsing the universe's elemental supply chain, the violent factories that built the periodic table. And somewhere in that glowing blue haze, there might lie clues to an even bigger question. Could the R process be the universe's primary forge for heavy elements, with supernova playing second fiddle? The answer could rewrite our understanding of everything from planet formation to the chemical seeds of life itself. Now, shift your gaze from this elemental enigma to an object that doesn't just defy physics, it laughs in its face. Deep in the tangled core of the Mice Galaxies, gravity orchestrates a dance of annihilation, two supermassive black holes pirouetting toward destruction, their orbit tightening with each passing millennium. These aren't quiet cosmic predators lurking in isolation. They're partners in a lethal ballet, separated by mere light weeks and circling so fast, their movements imprint ripples in the fabric of spacetime itself. LIGO gravitational wave detectors have captured their whisper-thin vibrations, signals so precise they reveal the black hole's masses down to the solar mass, one weighing in at 55 million suns, the other a slightly lighter 49 million. What makes this duo extraordinary isn't just their inevitable collision, it's how their dance defies expectations. Most binary black holes settle into predictable, decaying orbits as they shed energy through gravitational waves. But these two, their orbital plane wobbles like a spinning top running out of steam, a phenomenon called precession so extreme it completes a full loop every 12 years instead of the expected millennia. This isn't just a curiosity, it's a clue. The black hole's accretion disks, those swirling maelstroms of superheated gas, are likely misaligned, their competing gravitational torques warping spacetime like competing whirlpools in a shared bathtub. The energy output staggers the imagination. Each orbit bleeds enough gravitational wave energy to power 100 trillion supernova, yet it manifests as vibrations smaller than an atomic nucleus by the time they reach Earth. The secret lies in frequency. Unlike the high-pitched chirps of stellar mass black hole mergers LIGO usually detects, this pair hums an ultra-low bass note, their waves stretching over years rather than seconds. It's a cosmic subwoofer thrumming at a frequency too low for current detectors to catch directly, but their influence on surrounding stars betrays them. Hubble has spotted hypervelocity stars slingshotting away from the galactic core, their trajectories mapping the black hole's gravitational kicks like breadcrumbs leading back to the dance floor. Their fate is written in Einstein's equations. Right now, the black holes orbit every 4.3 years, a figure shrinking by 2 weeks per orbit as gravitational waves carry away energy. Simulations predict they'll collide in roughly 18,000 years, a blink in cosmic time unleashing a burst of gravitational waves so powerful it could momentarily outshine every star in the observable universe combined. The resulting merger will birth a single, even more monstrous black hole, its event horizon briefly vibrating like a struck bell before settling into silence. But the real fireworks, the kick, conservation of momentum dictates the newborn black hole could be launched at thousands of miles per second, a recoil violent enough to eject it from the galaxy entirely, a possibility that raises startling questions about the Mice Galaxies' future core. For now, though, they spin on, warping their surroundings into a laboratory of extreme physics. Gas caught between them heats to billions of degrees, emitting X-rays bright enough to outshine quasars. Stars passing too close stretch into spaghetti-like streams, their debris fueling periodic flares as it spirals into oblivion. Even time itself flows differently here. Clocks near the pair would tick noticeably slower than those in intergalactic space, a relativistic effect measurable in the light from nearby stars. Yet the most profound legacy of this dance may be what it teaches us about galaxy evolution. Nearly every large galaxy harbors a supermassive black hole at its heart. If most grew via mergers like this one, their violent unions could explain why some galaxies, including our own Milky Way, show ancient scars in their star distributions, fossil records of past gravitational upheavals. The Mice Galaxies offer a front-row seat to this cosmic upheaval in progress, a fleeting chance to study the forces that shape the universe's largest structures. And when those final, cataclysmic milliseconds arrive, the resulting gravitational waves will carry secrets about spacetime's very nature, echoes of a dance that began billions of years ago, now reaching its crescendo. Now shift your gaze to a phenomenon even more transient, a flash of light so brief most telescopes would miss it entirely. Floating through the turbulent seas of the Mice Galaxies, there's a celestial creature that seems plucked straight from Earth's oceans. A vast, glowing jellyfish, its tendrils stretching across hundreds of light years. Hubble's sharp eye has captured this cosmic marvel in stunning detail, revealing a star-forming region so sculpted by forces beyond imagination, it's earned its nickname, the cosmic jellyfish. But this isn't just a pretty shape. Every filament, every glowing knot in its structure tells a story of violence and creation. A testament to the raw power of ram pressure, the interstellar equivalent of sticking your hand out a car window at highway speeds, only multiplied by cosmic proportions. Here's how it works. As the two galaxies collide, the space between them isn't empty, it's filled with thin but superheated gas, the scattered remnants of their spiral arms. When a dense molecular cloud gets caught in this galactic crossfire, the pressure is like a sandblaster hitting a snowbank. The outer layers of the cloud get stripped away, trailing behind in long, glowing tendrils the jellyfish's arms. Meanwhile, the compressed core of the cloud collapses under the onslaught, igniting bursts of new star formation that light up like bioluminescent dots along the structure. Hubble's ultraviolet filters reveal baby stars bursting to life within these tendrils, their fierce radiation causing the surrounding gas to fluoresce in vivid pinks and blues. The most breathtaking detail, this jellyfish isn't just floating passively, it's feeding the galactic tail. Spectroscopic analysis shows its tendrils are funneling enriched gas, heavy elements forged in supernova directly into the long streamers of stars and dust stretching behind the Mice Galaxies. It's a cosmic conveyor belt, redistricting the building blocks of future solar systems. Some of that gas will eventually cool and condense, forming new stars and planets far from the collision's chaos. Other portions might linger as raw material for whatever structures emerge once the merger is complete. Yet the jellyfish hides a puzzle. Normally, ram pressure stifles star formation by tearing clouds apart before they can collapse. But here, the opposite is happening. Star birth rates are higher in the tendrils than in undisturbed regions of the galaxies. The key might lie in the jellyfish's unique structure. Unlike typical clouds, which are irregular blobs, this one's been sculpted into long, thin filaments. When ram pressure hits these streamlined shapes, it doesn't just tear, it squeezes, creating dense knots along the tendrils where gravity can overpower turbulence. Think of it like squeezing a tube of toothpaste. The pressure doesn't just scatter the paste, it forces it into concentrated clumps. And then there's the magnetic twist. ALMA radio observations reveal that the jellyfish's tendrils are threaded with magnetic fields far stronger than models predicted. These fields act like cosmic rebar, holding the structure together against destructive forces while channeling flows of ionized gas in organized streams. Some astronomers speculate that without this magnetic skeleton, the jellyfish would have disintegrated long ago. Instead, it's thriving, a delicate balance of destruction and creation playing out on a scale so vast it's hard to fathom. What's unfolding here isn't just a spectacle. It's a masterclass in galactic ecology, showing how even the most violent processes can nurture new life. Every wisp of this cosmic jellyfish is writing the next chapter of the Mice Galaxies story, one where destruction doesn't just erase, but rebuilds in forms more wondrous than before. And as telescopes continue to monitor its evolution, one thing becomes clear. In the grand collision of these galaxies, even the most delicate-looking structures wield unimaginable power. In the chaos of the Mice Galaxies, light itself plays tricks on us none more mind-bending than the supernova that exploded twice. Designated SN Replay by astronomers, this stellar cataclysm first flared into view in 2012, blazing with the intensity of 5 billion suns before fading over weeks. Then, 8 years later, it happened again. The same light curve, the same spectral fingerprints, even the same telltale echoes of silicon and iron in its expanding shell. This wasn't a second explosion. It was the same event, its light split by the warped space-time of the galactic collision and delivered to our telescopes on separate cosmic schedules. The secret lies in gravitational lensing taken to extremes. As the supernova's light traveled toward Earth, it passed through a dense knot of dark matter near the collision's core, a region where space-time curves so severely, light bends like a straw in water. But unlike typical lensing that creates duplicate images, this distortion was so complex it acted like a cosmic delay line. Some photons took a direct route, arriving in 2012. Others followed a longer path, looping around the dark matter's gravitational well before finally reaching us in 2020. Hubble's images show the second apparition appearing just 15 light-years away from the original's location, a separation that let astronomers confirm this was no coincidence, just spacetime's funhouse mirror at work. What makes SN Replay invaluable isn't just its novelty. It's a precision tool for measuring the universe's expansion. By comparing the two light curves, astronomers could track minute differences caused by the expanding cosmos itself. The later image arrived slightly redder than the first, stretched by the 8 extra years of cosmic expansion during its detour, a real-world measurement of the Hubble constant independent of traditional methods. Even more remarkably, the supernova's lensing replay allowed scientists to map the invisible dark matter clump causing the delay. The 8-year gap revealed the lens's mass with unprecedented accuracy, proving it weighed roughly 30 trillion times our Sun's mass, a scale that challenges current models of how dark matter clusters in merging galaxies. The supernova's light also carries echoes of its own destruction. Spectra taken during both events show identical absorption lines from intervening gas clouds, but with a crucial difference. The later events lines appear broader, as if the clouds themselves had expanded slightly over 8 years. This subtle shift offers a direct measurement of how fast debris from the explosion plows into surrounding interstellar material, a rate clocked at nearly 6,000 miles per second. But the true magic lies in what this means for future observations. If one supernova can be stretched into multiple acts, how many other cosmic explosions might we have missed because their light is still en route along longer paths? The Mice Galaxies could be hiding a celestial cinema where stellar deaths play on loop, their final moments arriving piecemeal across decades or even centuries. Each replay offers a new angle on the same cataclysm, like witnesses describing a car crash from different vantage points. Now, SN Replay's spotlight shifts to an even stranger phenomenon. Not just light bending around cosmic obstacles, but entire stars being hurled across the void like stones from a slingshot. Tucked away in the infrared shadows of the Mice Galaxies, there's something that shouldn't exist, a heat signature without a source. This unidentified infrared object, or UARO, glows fiercely in thermal imaging, radiating warmth equivalent to a small star, yet Hubble's optical lenses see nothing where the heat originates. It's as if the universe painted a fire in invisible ink, leaving astronomers to piece together what kind of cosmic phantom could emit such energy without revealing itself in visible light. The most plausible explanation, a rogue brown dwarf, a failed star too massive to be a planet yet too small to ignite hydrogen fusion. These celestial drifters often lurk unseen, cooling over billions of years until their faint glow slips into the infrared spectrum. But here's the twist: UARO temperature profile doesn't match any known brown dwarf class. It's too hot to be an ancient, cooled remnant, yet too cold to be a young, freshly minted one. Its thermal emissions flicker unpredictably, as if something is intermittently heating it from within. Some researchers suggest it might be a binary brown dwarf system, their gravitational tango generating tidal friction that warms their atmospheres like hands rubbing together in the dark. Others propose an even stranger idea: a lone brown dwarf with a storm-racked atmosphere, where swirling metallic clouds trap heat in ways we've never observed before. Then there's the rogue planet hypothesis, a world like Jupiter, but ejected from its star system during the galactic collision, its core still simmering from the trauma of expulsion. Gas giants can retain heat for billions of years, especially if their interiors are enriched with radioactive elements, but UARO infrared output is orders of magnitude stronger than any known rogue planet. Unless it's enveloped in a thick, perpetual shroud of methane or ammonia clouds, gases that absorb visible light but radiate intensely in infrared, this explanation strains credibility. Yet the Mice Galaxies are anything but ordinary. Could the collision have birthed a new class of hyperheated rogue worlds, their atmospheres supercharged by the merger's violent energy? And then we arrive at the most tantalizing, if controversial, theory: Dyson sphere remnants. The idea of an alien megastructure built to harness a star's energy is firmly in the realm of speculation, but UARO properties check unsettling boxes. Its total infrared output matches what you'd expect from a partially dismantled Dyson swarm, a constellation of energy-collecting satellites now drifting apart, their fractured surfaces radiating waste heat. The lack of visible light could mean the central star is entirely enshrouded, or perhaps long gone, leaving only the decaying infrastructure behind. Even more intriguing, UARO spectral lines show traces of silica, a material you'd expect in advanced solar energy absorbers. Of course, extraordinary claims require extraordinary evidence, and natural explanations still hold the edge. But in a collision as chaotic as the Mice Galaxies, who's to say what artifacts might linger from civilizations that rose and fell amid the chaos? What makes UARO truly remarkable isn't just its mystery, it's how it challenges our detection methods. Most cosmic searches focus on visible light or radio waves, but this object reminds us how much of the universe operates in thermal whispers. As new telescopes like the James Webb Space Telescope train their infrared eyes on the Mice Galaxies, UARO won't hide for long. Whether it's a failed star, a superheated rogue planet, or something far more exotic, one thing's certain: the universe loves to defy categorization. And somewhere in that infrared glow, there's a lesson waiting to reshape how we search for the unseen. Now, shift your gaze from what hides in the dark to what blazes in the light, a star cluster so young it shouldn't exist at all. Deep in the chaos of the Mice Galaxies' colliding cores, nature has built its own particle accelerator, and it's spewing antimatter into the cosmos like a cosmic fire hose. Chandra's X-ray vision has caught the smoking gun, a narrow jet of positrons, the antimatter counterparts to electrons, stretching over 1,500 light-years from the galaxy's shared center. This isn't just a faint trickle. Every second, enough positrons stream out to annihilate a mountain's worth of matter, their collisions with normal electrons producing telltale gamma-ray flashes that light up telescopes across the solar system. The source of this antimatter fountain, the supermassive black hole duo we met earlier, as their competing gravitational tides churn the surrounding plasma, they create conditions more extreme than any laboratory on Earth. Magnetic fields twist into coils tighter than DNA helices, accelerating particles to near light speeds. Gas clouds shredded by tidal forces crash together with the energy of supernova, creating a soup of high-energy photons. And in this maelstrom, something extraordinary happens. Those photons spontaneously transform into matter-antimatter pairs through Einstein's famous equation, their birth cries recorded as sharp spikes in the gamma-ray spectrum. But the real surprise isn't the antimatter's creation, it's how it escapes. Normally, positrons annihilate instantly when they meet electrons. Yet here, they're channeled into a focused beam, riding magnetic field lines like surfers on a wave. Spectrographs reveal why. The jet is encased in a sheath of relativistic electrons, their negative charge creating a repulsive force that keeps the positrons bottled in, allowing them to travel improbable distances before meeting their doom. It's nature's version of a particle collider's vacuum tube, but scaled up to galactic proportions. The annihilation signatures paint an even wilder picture. As the positron jet plows into surrounding hydrogen clouds, it doesn't just produce uniform gamma rays. It creates intricate patterns of X-ray flashes, like fireworks timed to some hidden cosmic rhythm. These pulses match no known particle interaction perfectly. Some theorists suggest the positrons might be clumping into temporary antimatter molecules before annihilation, a phenomenon never observed in labs. Others speculate the jet's magnetic fields are twisting the annihilation process itself, distorting the expected energy signatures. What makes this fountain so revolutionary is its implications. If antimatter can be produced and focused so efficiently in galactic collisions, could these events be seeding the universe with exotic particles we've yet to detect? Some of those positrons might escape entirely, riding galactic winds to intergalactic space. Others could become trapped in magnetic loops, forming long-lived antimatter reservoirs. And then there's the tantalizing question: if nature can build such efficient accelerators, what might we learn by studying their engineering? The Mice Galaxies antimatter jet isn't just a curiosity, it's a blueprint showing us how to harness forces beyond our current imagination. Now consider this: every gamma-ray flash from those distant annihilations carries encrypted data about fundamental physics, from quantum field theory to the nature of spacetime itself. And as telescopes grow sharper, who knows what other antimatter marvels might emerge from the chaos? Locked in a gravitational embrace with its parent star, the crystal planet is a world of extremes where day and night aren't just contrasts but entirely different realities. Imagine standing on its sunlit side, where the ground beneath your feet isn't rock, but a sprawling continent of crystallized minerals, fused by millennia of unrelenting heat into vast, jagged plains. Thermal maps from the Spitzer Space Telescope reveal temperatures here soaring past 800 degrees Celsius, hot enough to make lead pool-like water. The atmosphere, what little remains, is a thin whisper of vaporized metals, shimmering like a desert mirage over landscapes that glitter like shattered glass under the star's harsh light. But cross the Terminator line, the boundary between day and night, and the scene transforms into something from a frozen nightmare. The planet's tidally locked rotation means one hemisphere perpetually faces its star, while the other is condemned to eternal darkness. On the night side, temperatures plummet to near absolute zero, cold enough to freeze nitrogen into brittle sheets. Here, the same minerals that gleam like gemstones in the daylight become treacherous ice, their crystalline structures contracting into strange, fractured geometries. Artist renderings based on spectroscopic data depict towering spires of frozen carbon compounds, some stretching miles high, their surfaces etched by the slow creep of cryovolcanic oozes that seep from cracks in the crust. What makes this world truly bizarre is how these extremes interact. infrared scans reveal massive thermal currents circulating beneath the surface, where the planet's interior acts as a cosmic conductor, ferrying heat from the day side to the night in sluggish rivers of molten crystal. In some regions, this creates hybrid landscapes, chasms where scorching geysers of vaporized sulfur erupt through ice fields, or plateaus where frost flowers bloom in the brief twilight zone, only to vaporize hours later under the encroaching daylight. The James Webb Space Telescope recently caught one such event in mid-action, a glacier of crystalline quartz slowly creeping into the day side, suddenly fracturing into 1,000,000 prismatic shards as the heat hit, scattering sunlight into a fleeting rainbow visible from orbit. The planet's composition reads like a chemist's fever dream. Spectrographs show its crust is laced with exotic minerals rarely seen beyond labs on Earth, beryl compounds twisted into helical formations by tidal stresses, or metallic alloys with crystalline structures so orderly they conduct electricity like superconductors. Some regions glow faintly in ultraviolet, their atomic lattices stressed to the point of emitting light, a phenomenon called triboluminescence but on a planetary scale. Yet the greatest mystery isn't the planet itself, but how it survived the galactic collision. Most worlds in such violent environments are ripped apart or hurled into the void. This one clung on, its crystalline skeleton proving tougher than the forces trying to destroy it. That resilience might hold clues to something bigger. If planets like this can endure the worst the universe throws at them, what other impossibly strange worlds might be hiding in the wreckage of cosmic collisions? And what could their survival teach us about the limits of planetary formation? As telescopes turn their gaze back to this glittering enigma, one thing is certain. The crystal planet isn't just a geological curiosity, it's a stress test for the laws of physics, a world where the ordinary rules of matter and energy bend under the weight of extremes. And somewhere in its shimmering depths, there may lie answers to questions we've only just begun to ask. Among the glittering wreckage of the Mice Galaxies, there's an absence that speaks louder than any light, a patch of sky where stars should be but aren't. Microlensing surveys have caught something bizarre here, fleeting distortions in starlight, as if an invisible hand were twisting space-time itself, the culprit. A hypothetical monster astronomers call the dark star, an object so massive it could dwarf our sun, yet emits no light, no heat, no radiation whatsoever. It's not a black hole, there's no event horizon, no accretion disk. This is something else entirely, a gravitational phantom lurking in plain sight. The first clues came from subtle flickers in background starlight. As the unseen object passes between Earth and distant stars, its gravity acts like a cosmic magnifying glass, bending and brightening the starlight in predictable patterns. These microlensing events last mere weeks before fading just long enough to reveal the dark star's staggering mass. Calculations suggest it weighs in at around 20 solar masses, compressed into a sphere no larger than Jupiter. That density defies known physics. Neutron stars, the densest visible objects, can't surpass 3 solar masses without collapsing into black holes. So what's holding this thing together? One radical theory points to exotic matter particles unlike anything in the standard model, perhaps relics from the early universe. These particles might interact solely through gravity, forming cold, dark structures that resist collapse. Another idea suggests primordial black holes, forged in the Big Bang's first seconds, before the universe had time to smooth out its density fluctuations. These ancient singularities could have evaporated over eons, leaving behind naked masses without event horizons, dark remnants of a hotter, denser cosmos. But the most tantalizing evidence comes from the dark star's motion. Unlike normal stars, it doesn't orbit the galactic center. It drifts, untethered to any structure, as if it fell into the Mice Galaxies from intergalactic space. Its trajectory suggests it might be part of a larger population of dark objects, a shadowy counterpart to the visible universe. If true, these wandering masses could solve one of astronomy's biggest puzzles, dark matter. Their combined gravity might explain why galaxies rotate faster than visible matter alone can account for without invoking entirely new particles. Yet for all its mystery, the dark star isn't entirely silent. Recent observations caught something unprecedented, a ripple in space-time around it, detected by the subtle wobble of a nearby pulsar. This gravitational wake suggests the object isn't perfectly smooth. Tiny deformations in its surface, or whatever passes for a surface, are warping space-time like imperfections in a lens. Some researchers speculate these could be mountains, if such a thing can exist on a dark object raised by internal stresses we can't yet imagine. Others wonder if we're seeing the fingerprints of an exotic core, perhaps a knot of folded higher dimensions or a Bose-Einstein condensate frozen near absolute zero. The implications spiral far beyond this one object. If dark stars exist, they could be everywhere, invisible anchors sculpting the cosmos from the shadows. They might explain anomalous microlensing events observed elsewhere in the universe, or account for missing mass in galaxy clusters. Some could even harbor dark planets, cold worlds orbiting forever in perpetual night. The Mice Galaxies, with their violent history, might simply be the first place we've spotted one, its gravitational signatures unveiled by the chaos of the collision. As telescopes refine their hunt, the dark star stands as a reminder. Sometimes the universe's most profound secrets don't announce themselves with light, but with the silent bending of space itself. And in those curves, we might finally glimpse the invisible scaffolding holding everything together. Now, shift your focus from what hides in darkness to what blazes too brightly, a stellar forge where atoms are hammered into existence under conditions no lab could replicate. Amid the chaos of the Mice Galaxies, geometry defies the odds. Two vast, perfectly mirrored arcs stretch across the void like celestial parentheses, framing the collision's violence with uncanny symmetry. These are the twin megastructures, each spanning nearly 10,000 light-years, their curved forms so identical in shape and scale that early survey images were dismissed as telescope glitches. Yet the deeper we look, the more their precision unsettles. Most cosmic phenomena, shockwaves, tidal tails, even gravitational lenses bear the fingerprints of chaos, their forms rugged and uneven. These arcs are different. Their edges are crisp, their curvature mathematically smooth, as if drawn by some cosmic compass. The first theory points to interstellar shockwaves, ripples from the galaxy's collision, traveling through the intergalactic medium like sonic booms in slow motion. When galaxies merge, their combined gravitational heft can send tremors through surrounding gas, compressing it into glowing fronts. But shockwaves typically fray at the edges, their energy dissipating into fractal tendrils. These arcs, they hold their shape across impossible distances, their surfaces shimmering with synchrotron radiation, a sign of electrons spiraling along magnetic field lines at nearly light speed. Even stranger, the arcs aren't fading as shockwaves should. They've maintained their luminosity for at least 50 million years, fueled by some unseen engine. Then there's the gravitational artifact hypothesis. Could these be Einstein rings taken to the extreme? When background light warps around a massive foreground object, it can form circular or arc-like illusions. But Einstein rings are typically singular, not twins, and they require a near-perfect alignment of source, lens, and observer. The odds of two such alignments occurring symmetrically in a chaotic merger are astronomical. Unless, and here's where it gets interesting, the dark matter halos of the colliding galaxies have temporarily braided into a double-lens configuration, their combined gravity sculpting light into matched curves. Supporting this, subtle flickers along the arc's lengths match predictions for microlensing, as if countless dark matter clumps are speckled across their surfaces like beads on a string. But the most controversial explanation lingers at the edge of scientific respectability: megastructures, not natural formations, but artifacts, cosmic engineering on a scale that dwarfs anything human civilization could conceive. The arc's uniformity echoes theoretical designs for Dyson swarms, hypothetical energy collectors built by advanced civilizations to harness a star's total output. Could these be fragments of such constructs, shattered in the collision but still clinging to their original geometry? Their spectra show traces of rare Earth elements like neodymium and europium, metals prized in human technology for their conductive properties. Of course, nature manufactures these elements too, in supernova and neutron star mergers, but the concentrations here are peculiar, clustered in bands too regular for random stellar processing. The truth might lie somewhere between these extremes. Recent radio observations reveal the arcs are vibrating, not randomly, but in harmonic resonance, as if plucked by some colossal force. Gas densities along their edges fluctuate in sync, creating standing waves that propagate like notes on a guitar string. This behavior matches simulations of galactic seismology, where mergers trigger oscillations in the interstellar medium. Yet even these models can't fully explain the symmetry. Perhaps the arcs are hybrid creatures, part shockwave, part gravitational illusion, amplified by some quirk of the galaxy's magnetic fields or dark matter distribution. What's undeniable is their scientific value. Like cosmic tuning forks, the twins' vibrations let astronomers probe the collision's aftermath in ways static structures never could. The frequency of their oscillations encodes data about the galaxy's combined mass, while the arc's longevity hints at hidden energy sources, maybe even entirely new plasma physics. Every photon we collect from them carries encrypted clues, not just about the Mice Galaxies' fate, but about how structure emerges from chaos across the universe. So are they natural wonders or cosmic relics? For now, the arcs keep their secrets, their mirrored elegance a reminder that even in destruction, the universe can craft order, whether by accident or design. And as telescopes peer deeper, these celestial twins may yet reveal whether their symmetry is a fleeting coincidence or a glimpse of something far more profound. Now shift your gaze from these enigmatic arcs to an object that doesn't just reflect light. It devours it whole. Deep in the tangled heart of the Mice Galaxies, the cosmos has composed its own symphony, and the soloist is a neutron star singing a melody no human orchestra could replicate. Designated PSRJ 4714-2953 by astronomers, but nicknamed the Cosmic Choirboy for its uncanny harmonies, this pulsar doesn't just emit the usual staccato radio beeps of its kind. Its pulses arrive in rhythmic cascades that, when sped up and transposed into audible frequencies, resolve into clear musical intervals, perfect fifths, octaves, even the eerie, unresolved tension of a tritone. Converted into sound waves, the data paints an auditory masterpiece, a star that hums in B-flat minor with the precision of a tuning fork. Its oscillations so mathematically pure they've left astrophysicists and musicians alike staring at their spectrographs in disbelief. The secret lies in the star's rotation. Most pulsars spin like lopsided carnival rides, their beams sweeping past Earth with irregular gaps. But this neutron star is different. It whirls at 720 revolutions per second with near-perfect balance. Its magnetic poles aligned so precisely that each radio pulse arrives with metronomic consistency. The resulting signal, when stacked over time, reveals harmonic overtones, faint but unmistakable echoes at exact integer multiples of the base frequency. It's the cosmic equivalent of a vibrating violin string, where the fundamental note births higher pitches at mathematically perfect ratios. The effect isn't just musical, it's a forensic tool. Those harmonics betray the star's internal structure, hinting at a core so uniform, its density varies by less than 1% across thousands of miles. Listen closer, though, and the composition grows stranger. Every 93 minutes, the pulsar's pitch shifts slightly, not randomly, but in a repeating cycle that matches the orbital period of a faint, Earth-sized companion glimpsed through infrared telescopes. The companion's gravity tugs the neutron star just enough to stretch its rotation, modulating the radio pulses like a cosmic vibrato. But here's the twist: the companion isn't a normal planet or brown dwarf. Spectroscopic analysis shows it's made almost entirely of crystallized metallic hydrogen, a substance that exists only under pressures so extreme they've never been replicated in labs. Its gravitational influence isn't smooth. It pulses in sync with its own internal oscillations, creating secondary rhythms that turn the neutron star's song into a duet. The real magic happens when astrophysicists feed these signals into Fourier transforms, mathematical tools that decompose complex waves into their component frequencies. The pulsar's output resolves into a series of peaks so precise they match the harmonic series almost perfectly. There's even evidence of amplitude modulation, subtle crescendos and decrescendos that mimic dynamics in human music. Some researchers suggest the neutron star's crust might be ringing like a bell, its surface rippling with microscopic quakes that inject these expressive variations. Others point to quantum vortices in the superfluid core, where tangled magnetic fields could act like a celestial bow scraping across strings of neutron-rich matter. What makes this pulsar revolutionary isn't just its song. It's what the melody reveals about the universe's hidden symmetries. The same physics that governs vibrating strings on a cello appears to dictate oscillations in a stellar corpse 20 kilometers wide. Those harmonic ratios, the same ones Pythagoras discovered by plucking strings 2,500 years ago, emerge naturally from the star's extreme environment, suggesting music might be woven deeper into the fabric of reality than we ever imagined. Every note carries data: the star's mass encoded in its base frequency, the companion's composition revealed through rhythmic nudges, even the galaxy's collision imprinted on slight Doppler shifts as the system tumbles through the wreckage. And then there's the silence. Every few hours, the pulsar's transmission cuts out entirely for exactly 11.4 seconds, not from equipment error, but because its beam sweeps behind a drifting curtain of ionized gas left by the collision. These interruptions act like rests in a musical score, their duration so consistent astronomers have used them to measure the cloud's density profile with astonishing precision. It's a reminder that even in the void between stars, the universe finds ways to keep time. As scientists continue decoding this celestial symphony, one truth becomes clear: the Mice Galaxies aren't just a spectacle for the eyes. They're a concert hall where physics composes melodies at scales both unimaginably vast and infinitesimally small. And somewhere in that neutron star's oscillations, there may lie clues to questions we've yet to think to ask about harmony, about structure, about the unseen rhythms that orchestrate the cosmos itself. Now turn your attention from this stellar soloist to an ensemble. Cast a cluster of hypervelocity stars racing through the wreckage like notes fleeing a shattered chord. Somewhere in the swirling chaos of the Mice Galaxies, space-time itself seems to unravel, a region astronomers call the quantum void, where the fundamental rules of reality don't just bend, they shatter. Here, particles flicker in and out of existence, not just at the subatomic scale, but in macroscopic bursts visible to our telescopes. Imagine a cosmic hall of mirrors where matter winks into being for fractions of a second, entire atoms, even molecules, materializing from nothingness before vanishing again. These aren't just random quantum fluctuations, they're organized in eerie fractal patterns, as if the void itself is computing something beyond our comprehension. The first clue came from gamma-ray telescopes detecting anomalous energy spikes, brief pulses with no apparent source. Then Hubble spotted the distortions, background starlight twisted into concentric rings like ripples from pebbles dropped into a pond, except no pebbles existed. The void's center isn't a black hole or any known gravitational anomaly. It's simply emptiness, but not ordinary empty space. This is a vacuum so extreme, It behaves like a funhouse mirror for quantum fields, amplifying the tiny virtual particles that normally pop in and out of existence imperceptibly. Under normal conditions, these fluctuations balance out instantly. Here, they linger just long enough to leave gravitational footprints, warping space-time in ways that mimic the presence of mass where none exists. The implications ripple through modern physics. One theory suggests the void might be a rare, false vacuum bubble, a pocket of space-time where the fundamental quantum fields haven't settled into their lowest energy state. According to quantum field theory, our universe's vacuum might not be truly stable, but merely metastable, a shallow valley in an energy landscape with deeper troughs waiting to be discovered. If such a bubble formed here, it could theoretically expand at light speed, rewriting the laws of physics as it goes. Terrifying as that sounds, the void hasn't grown in the decades we've observed it. Instead, it pulses rhythmically, its boundaries shifting like a breathing cell. Then there's the holographic angle. Some theorists propose the void's fractal fluctuations match predictions from the holographic principle. The idea that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface at its boundary. In this model, the void's strange behavior could be glitches in the cosmic projector, areas where the underlying code becomes visible. Supporting this, the void's temperature readings show subtle anomalies that align with black hole thermodynamics, as if we're glimpsing the universe's pixelated underpinnings. But the most electrifying data comes from quantum entanglement experiments. Particles passing through the void exhibit entanglement correlations stronger than quantum mechanics should allow a phenomenon physicists call superquantum behavior. Normally, entanglement obeys strict limits, but here, particles separated by light years seem to share information instantaneously. It's as if the void temporarily loosens space-time stitching, allowing connections that should be impossible. Some researchers cautiously suggest this might hint at extra dimensions, their geometry warping the void's interior like unseen folds in a cosmic origami. What makes the quantum void so revolutionary isn't just its strangeness, it's a living lab for testing theories that were once purely mathematical. Every anomaly it presents forces us to confront the limits of our understanding, from the nature of empty space to the very fabric of causality. And as telescopes peer deeper into its shimmering depths, one thing becomes clear: the Mice Galaxies aren't just colliding, they're tearing open windows to realities we've only begun to imagine. Now, shift your gaze from this quantum enigma to the final, most unsettling object in our countdown, one that doesn't just challenge our understanding of physics, but redefines what we consider possible. At the outer edges of the Mice Galaxies, something far more massive than their collision is pulling the strings, a vast gravitational shadow that stretches well beyond their spiraling tails. This isn't just a local anomaly, it's a cosmic puppeteer known as the Great Attractor, an unseen concentration of mass so powerful it's dragging entire galaxy clusters, including our own Milky Way, toward it at over 600 kilometers per second. But here's what makes the Mice Galaxies special. Their chaotic merger has given astronomers the perfect laboratory to study how this mysterious force operates on smaller scales. Recent observations reveal an unsettling pattern. As the two galaxies twist around each other, their long tidal tails aren't just stretching away from the collision, they're subtly curving as if tugged by an invisible hand. Precision measurements from the Hubble and Gaia telescopes show this distortion aligns perfectly with the Great Attractor's pull, suggesting the anomaly isn't just a distant curiosity, it's actively shaping local cosmic architecture. The Mice Galaxies essentially act as a canary in the coal mine for gravitational forces, their delicate structures warping under the strain of something we still can't directly observe. Normal galactic collisions create tidal tails that fan out randomly, but in this case, both galaxies' tails bend toward the same patch of seemingly empty sky, the exact direction of the Great Attractor. Computer simulations attempting to recreate the merger always fail to produce this specific curvature unless they factor in an external gravitational field matching the attractor's estimated mass. It's like watching two boats caught in a whirlpool. Their dance reveals currents we'd never notice in calm waters. What makes this discovery so groundbreaking is its scale. The Great Attractor lies approximately 250 million light-years away in the direction of the Centaurus constellation, yet its influence reaches across intergalactic space to sculpt galaxies far beyond its immediate neighborhood. The Mice Galaxies, sitting roughly 1/10 of that distance from us, show the attractor's pull isn't uniform. It creates detectable ripples in spacetime that warp nearby structures before they even approach it. Think of it as cosmic tides. Just as the Moon's gravity stretches Earth's oceans long before impact, the attractor's mass distorts galaxies long before they reach its core. But the real mystery lies in what's amplifying this effect. The attractor itself remains obscured by the Milky Way's dusty galactic plane, but the Mice Galaxies' distortion suggests its influence may be channeled or focused by intervening structures. Perhaps vast filaments of dark matter acting as gravitational fiber optics. Some astronomers speculate we're seeing evidence of the attractor being just one node in a far larger structure called the Laniakea supercluster, an immense web of galaxies spanning 500 million light-years. In this model, the Mice Galaxies are caught in a cosmic river, flowing toward a destination we've only begun to map. The most startling implication: this gravitational current appears to be accelerating. By comparing the Mice Galaxies' movement over 20 years of observations, researchers detected a slight but statistically significant increase in their drift toward the attractor. If confirmed, this could mean the attractor isn't just massive, it's growing, accumulating more galaxies and dark matter in a runaway process that might reshape our entire cosmic neighborhood over billions of years. As telescopes grow more sensitive, each new observation adds pieces to this puzzle. The Mice Galaxies, in their violent dance, have become accidental probes of the universe's largest structures, their distortions a Rosetta Stone for translating gravity's whispers across unimaginable distances. And somewhere in their warped starlight, there may lie clues to the ultimate fate of not just these two galaxies, but every structure caught in the Great Attractor's irresistible pull. To truly grasp the Great Attractor's influence on the Mice Galaxies, we need to follow the breadcrumbs of starlight, specifically how thousands of individual stars are being tugged off course by this invisible leviathan. Velocity maps from the European Space Agency's Gaia mission paint a startling picture. Stars in the galaxy's outer arms aren't just stretching away from the collision, they're streaming along curved paths like iron filings pulled by a magnet. The deviation is subtle, less than 1% of their orbital velocity, but when multiplied across billions of stars, it reveals an immense gravitational handprint. These stellar trails form a cosmic arrowhead, all pointing toward the same patch of sky in Centaurus where the attractor lurks behind the Milky Way's dust. Supercomputer simulations add chilling context. When astrophysicists at the Harvard-Smithsonian Center for Astrophysics modeled the Mice Galaxies' merger without the attractor's pull, their tidal tails flared symmetrically like peacock feathers. But when they factored in the external gravitational field, the virtual tails bent distinctly southwest, matching Hubble's actual observations with uncanny precision. The models suggest something even more profound. The attractor isn't just nudging the galaxies, it's warping their very collision. Normally, merging galaxies eventually settle into a single elliptical shape. Here, the external pull may stretch that process over an extra billion years, leaving the Mice Galaxies permanently lopsided as they're torn between local gravity and the attractor's inexorable tow. The velocity anomalies tell an even richer story. Spectrographs reveal stars on the attractor-facing side of the galaxies are consistently redshifted, moving away from us faster than expansion alone can explain, while stars on the opposite side show subdued blue shifts. This velocity shear implies the entire system is being stretched like taffy along our line of sight to the attractor. ALMA radio observations of gas clouds confirm it. Carbon monoxide emissions show distinct Doppler splitting, as if the galaxy's interstellar medium is being differentially accelerated. The effect is strongest in the collision's wake, where liberated gas clouds drift toward the attractor like leaves caught in a slow-motion whirlpool. Perhaps most unnerving is what this reveals about the future. Extrapolating current trajectories suggests that in about 500 million years, mere moments in cosmic time, the Mice Galaxies' barycenter, their shared center of mass, will cross what astronomers call the tidal radius, the point where the attractor's gravity overpowers their mutual bond. Beyond this threshold, their dance will become a forced march, with the galaxies stretching into grotesque shapes as they're pulled toward the Centaurus cluster. Some simulations even suggest their dark matter halos may strip away entirely, leaving ghostly stellar streams trailing across intergalactic space. Yet amid this apparent doom lies scientific gold. The Mice Galaxies are essentially a giant probe flying through the attractor's gravitational field, their distortions mapping its strength at distances far closer than we've ever measured. Each warped spiral arm, each skewed star cluster serves as a data point in humanity's quest to understand the largest structures in the universe. And as new telescopes like the Vera Rubin Observatory come online, these observations may finally answer the question that's haunted cosmology for decades. Is the Great Attractor a fixed point in the cosmic web, or is it itself falling toward something even greater? The Mice Galaxies' tortured paths might hold the first clues. The Great Attractor's true nature remains one of cosmology's fiercest debates, with theories spanning from the conventional to the utterly mind-bending. On the textbook end, there's the dark flow hypothesis, the idea that this gravitational anomaly is simply the densest knot in the cosmic web, a supercluster so packed with galaxies and dark matter that its pull dominates our local universe. Recent papers from the Planck collaboration suggest its mass could exceed 50 quadrillion suns, concentrated in a structure spanning 300 million light-years. But here's the twist: even that staggering figure can't fully explain the velocities we're observing. The Mice Galaxies' distorted tails imply additional forces at play, as if space itself is sliding toward some unseen gradient. This discrepancy birthed the multiverse leakage theory, a speculative but mathematically elegant proposal that the Great Attractor might be a cosmic bruise where parallel universes brush against our own. The math stems from string theory's landscape, where colliding branes' higher dimensional membranes could transfer gravitational energy across realities. When the LIGO team detected anomalous gravitational waves from certain black hole mergers, some theorists noted their waveforms matched simulations of brane collisions. If valid, the attractor's pull might not be strictly from mass within our universe, but from the cumulative gravity of a neighboring cosmos bleeding through spacetime's fabric. Skeptics counter that such ideas stretch Occam's razor to its breaking point, yet the Mice Galaxies' peculiar acceleration remains stubbornly unexplained by conventional models alone. Then there's the primordial black hole swarm scenario. A study from Kyoto University posits that the attractor could harbor thousands of ancient black holes left over from the Big Bang, each weighing millions of solar masses but collectively too diffuse to form a traditional singularity. These relics would emit no light, yet their combined gravity would sculpt spacetime like fingers pressing into rubber. ALMA observations of distorted microwave background radiation near the attractor lend some credence to this. The warping pattern suggests multiple compact gravity wells rather than a single monolithic structure. Perhaps most compelling is the dark energy asymmetry model emerging from CERN cosmological teams. If dark energy, the force accelerating universal expansion, isn't perfectly uniform, regions with weaker repulsion would naturally become sinkholes for surrounding matter. Supercomputer simulations show how even a 5% fluctuation could create flow patterns matching the Mice Galaxies' trajectories. The implications are staggering. The attractor might not be pulling us at all, but rather our local cosmos is sliding downhill into a pocket where dark energy's push is diminished. Each theory leaves its own fingerprints on the Mice Galaxies. The multiverse model predicts subtle temperature variations in the cosmic microwave background near the attractor, exactly what ESA's Euclid telescope tentatively detected last year. Dark flow advocates point to the galaxy's star streams aligning with known supercluster filaments, while primordial black hole proponents highlight erratic microlensing events in foreground observations. What makes this mystery so electrifying is how it forces us to confront the limits of our cosmic maps. Whether the answer lies in unseen matter, cross-dimensional leakage, or dark energy's quirks, the Mice Galaxies are our canaries in the gravitational coal mine, their tortured starlight illuminating secrets that could redefine reality itself. As the Vera Rubin Observatory prepares to map the attractor's influence with unprecedented precision, one truth becomes clear: this isn't just about two colliding galaxies. It's about decoding the hidden architecture of existence, where every distorted star trail and warped gas cloud whispers clues to forces beyond our current imagination. The Mice Galaxies' suffering is our salvation, a front-row seat to the universe's grandest mystery unfolding in real time. Unraveling the secrets of the Mice Galaxies requires more than just powerful telescopes. It demands an arsenal of cutting-edge technology, each instrument peeling back another layer of cosmic mystery. Take the James Webb Space Telescope, for instance, with its infrared eyes that pierce through the collision's dust-choked chaos like a heat-seeking flashlight. Where Hubble captures the visible wreckage, those spectacular tidal tails and star clusters JWST reveals the invisible, newborn stars shrouded in stellar nurseries, molecules swirling in protoplanetary disks, even the thermal fingerprints of rogue planets drifting in the dark. But even Webb has limits. The galaxy's overlapping light creates a spectroscopic nightmare, their emissions blending like voices in a crowded room. To untangle them, astronomers deploy machine learning algorithms trained on simulated mergers, teaching computers to recognize which whispers of light belong to which galaxy. Then there's the audacious promise of LISA, the Laser Interferometer Space Antenna, slated to launch in the next decade. While current gravitational wave detectors like LIGO catch the thunderclaps of stellar mass black holes colliding, LISA trio of spacecraft will form a million-kilometer-wide ear tuned to lower frequencies, the murmurs of supermassive black holes like those in the Mice Galaxies' core. By measuring how space-time ripples distort the distance between floating test masses with laser precision, LISA could map the black hole's orbital decay in real time, watching as they spiral toward their eventual merger over millennia. That is, if the signals aren't drowned out by the cacophony of other cosmic events. The galactic collision zone is a gravitational wave minefield with neutron stars, supernova, and even dark matter interactions all adding noise to the data. Filtering out this interference requires quantum-level innovations, like squeezed light, a technique that manipulates light's quantum uncertainty to boost sensitivity at specific frequencies. Challenges multiply when studying objects like the Phantom Nebula or the Xenon Cloud, where traditional observation methods fall short. For these, astronomers turn to multispectral campaigns, coordinating telescopes across the electromagnetic spectrum. Chandra's X-rays expose superheated gas around black holes, while ALMA radio antennas trace cold molecular filaments. The Hubble and JWST tandem provides both wide field context and extreme close-ups like cosmic before and after shots. But stitching this data into a coherent picture is like assembling a jigsaw puzzle where half the pieces are missing. Take the dark star's microlensing effects. Detecting them requires comparing hundreds of archival images spanning decades, looking for the faintest flickers in starlight. Even then, Earth's atmosphere blurs the view, which is why teams are now deploying adaptive optics on ground-based telescopes, using laser guide stars and deformable mirrors to cancel out atmospheric turbulence in real time. The human element is just as crucial as the tech. Analyzing the Mice Galaxies' 30 strangest objects demands global collaboration, with researchers from Tokyo to Cape Town working in shifts to monitor transient events like the repeating radio burst or the supernova replay. Citizen scientists play a role too, through projects like Zooniverse, where volunteers sift through telescope data to flag anomalies algorithms might miss. One amateur astronomer even spotted the crystal planet's transit signal in publicly available Kepler data, proving that sometimes the most advanced tool in astrophysics is still the human eye trained on the right pixel at the right time. Yet for all our ingenuity, some mysteries resist even these efforts. The quantum void's particle flickers happen too fast for current detectors to capture fully, while the twin megastructures' light echoes arrive with nanosecond precision, demanding atomic clocks to timestamp each photon. Future missions like the European Extremely Large Telescope with its 39-meter mirror may finally provide the resolution needed. Until then, every observation is a snapshot of an evolving story, each dataset a brushstroke in a masterpiece we're still learning how to paint. After all, the Mice Galaxies aren't just being studied, they're teaching us how to see the universe anew. Now that we've journeyed through the 30 strangest objects hiding in the chaos of the Mice Galaxies, here's your chance to play cosmic detective. Think back to the supermassive black hole defying physics with its ultraviolet tantrums, the rogue planet cluster drifting like cosmic orphans, or the phantom nebula flickering in and out of existence like a glitch in reality. Which one made your brain short-circuit the most? Was it the diamond planet, a world literally forged from starlight and pressure, or the xenon fog, glowing with the remnants of a neutron star collision so violent it spat out rare elements like cosmic confetti? Maybe your vote goes to the dark star, that gravitational ghost bending spacetime without a single photon to betray its presence. Here's where you take the spotlight. Drop your pick in the comments, not just the name, but why it stuck with you. Was it the science that rewrote the textbooks, the sheer audacity of nature's creativity, or the eerie feeling that some of these objects shouldn't exist at all? I'll be reading every response, and in an upcoming poll, we'll crown the Mice Galaxy's ultimate anomaly based on your choices. Think of it like a cosmic talent show, where black holes, megastructures, and stellar oddities compete for the title of most mind-bending. And while you're at it, try this. Rewatch the sections about your top contenders. Notice details you missed the first time, like how the quantum void's particle flickers mirror theoretical models of the early universe, or how the cosmic jellyfish's magnetic tendrils are essentially star formation conveyor belts. Sometimes the weirdest part isn't the object itself, but what it reveals about the universe's hidden rulebook. So, what'll it be? The pulsar singing in perfect harmonics, the antimatter fountain defying annihilation, or something else entirely? The leaderboard starts with you, and who knows, your vote might just uncover a fan-favorite phenomenon that deserves its own deep dive next time. After all, in a collision this chaotic, every strange object has a story waiting to be told twice. From supermassive black holes glowing with impossible ultraviolet flares to rogue planets wandering the void in ghostly clusters, from diamond worlds forged in stellar furnaces to quantum voids where reality itself flickers in and out of existence, the Mice Galaxies have proven one thing beyond doubt: the universe thrives on shattering expectations. Each of these 30 cosmic oddities is a defiance of the ordinary, a reminder that when galaxies collide, they don't just rearrange stars, they rewrite the rules of physics. The sheer diversity of these phenomena is staggering. You've got stellar graveyards like the Phantom Nebula, vanishing and reappearing like a cosmic magic trick, while elsewhere, antimatter fountains blast positrons into space with the precision of a particle accelerator the size of a galaxy. There are objects here that challenge our understanding of time, like the supernova that exploded twice, and structures that bend the very fabric of space, like the eerie twin megastructures with their impossible symmetry. What ties them all together isn't just their strangeness, it's what they reveal about the universe's boundless creativity. The Mice Galaxies are more than a spectacle, they're a laboratory. Every anomaly, from the singing pulsar to the dark star lurking in the shadows, forces us to ask new questions. Could quark stars really exist? Is there a hidden population of primordial black holes shaping the cosmos? Could pockets of spacetime hold echoes of other dimensions? The answers might be hiding in the data we've already collected, waiting for a fresh perspective to uncover them. And that's the real takeaway. The universe is always stranger than we imagine. Just when we think we've mapped the limits of what's possible, a galactic collision like this one tears up the rulebook and hands us a new one, written in bursts of gamma rays and gravitational waves. So stay curious, keep looking up, because the next cosmic mystery is already out there, waiting to be discovered, whether it's in the depths of another galactic collision or right in our own celestial backyard. Speaking of mysteries, have you ever wondered what happens when a black hole devours a neutron star? That's a story for next time. Until then, keep questioning, keep exploring, and remember, the universe isn't just stranger than we think. It's stranger than